Okay, let's continue now with our journey through entity relationship data modeling. And as we go through our discussion today, from time to time, I will make reference to this airline reservation application that I have used as a tool for my previous discussions as well. So first, let's take stock of where we are in this data modeling journey, and then we'll have a brief discussion of what we are about to discuss for today's presentation lecture, and then we'll get into the details. So first, let's take stock of where we are. So this data modeling journey, the start point and the end point, the starting point is some description of this airline application. So the this narrative is a description of the airline application. What are the various objects about which we have to store information, business rules by which operations take place, and so forth. And then the journey was summarized in this one slide. So starting from that narrative description about the business requirements, information requirements, the journey, the point in the journey where we are is that we have discussed this entity relationship model, this pictorial way of representing the structure of the database. So we are ultimately trying to end up with a description of the structure of the database in a way that can be implemented. And in that journey, where we are in that journey, is that we have discussed this entity relationship model represented by this picture, and we introduced all the concepts behind it and the constructs and what each of these symbols mean. What does the box mean? What does the line mean? What do these refinements of the line, this vertical bar and this crow's foot, what are all those things? What do they represent? So we have had a discussion of that. Now, the of the various components of the pictorial components of the entity relationship model. So this picture that you see is a conceptual representation of the logical models. It's the structure of the data in and it's called a logical model because it's independent of any physical implementation that will happen later. So this is a representation of the structure of the data given from the derived from the narrative, the description of the information needs of the business application. And now, in this next stage, that is in today's lecture, what we will discuss is how to take this logical model and take it a little closer to implementation. So, in this second phase over here, you can see that the entity airplane, the entity flight have been translated into relations. You've encountered the term relation before in our first lecture. So, and then within the entity you can see various attributes, details. So various details are being filled in. The relationships among the different entities, which were represented by lines as pictures in the logical model, and are now represented by other things, by attributes that connect one relation to another. You have seen this kind of connection in the very first lecture, for instance, when we tried to decompose one list into different themes that are related with one another. So we've had this discussion before, but the discussion that we are going to have today, that is in this journey about data modeling, what we are going to see is how does one go about taking this logical entity relationship diagram, which gives us a pictorial representation of the structure of the database, and get that structure, translate that into a form that is closer to implementation. Now, before we get into the nitty-gritty, so you can see that we are trying to fill in more details, and this process of translating the logical model, the logical ER diagram, to the physical model, you can see that it says it's the relational schema, because if you remember from the very first class, that the relational model represents a database as a collection of relations, interconnected relations. This is the relational schema. So there are a lot of details that need to be filled in. And as we go through our discussion of the translation of the logical entity relationship model to the physical model, we will see how to fill in the details. And today's particular lecture, we will focus on the entity and what goes into an entity, the different attributes, what are the details that need to be filled in, what are the little nuances and all of that. So that's what the discussion is going to be for today. Now, before we just get to that, let me just take a few minutes and wrap up our discussion of the logical model. So all the various pieces of the entity relationship model, the symbols and so forth, I want to recap that using an overall diagram about the airline reservation system, and try and reinforce the concepts and the symbols that we have introduced so far. And then we'll continue with our discussion of how to translate this logical model to the physical model. Okay, so here we have a more detailed representation of the logical model that might correspond to the airline reservation application that I've been using as a tool in my discussion. So all that this diagram represents is a more detailed version of this logical model that we've been using so far. So I'm going to use this diagram to reinforce concepts and symbols that have been introduced so far in describing the entity relationship diagram, the logical model. So you see these rectangles here, these boxes. These boxes represent entities. And if you were to drill down into each box, for instance, if you were to drill down inside crew, you would find that there are attributes that are properties of this entity crew. Similarly, if you drill down to reservation, this box, this is an entity, entities are represented by boxes. And if you were to drill down, you will find attributes that tell you something about the reservation. For instance, the date that the reservation was made, what was the price associated with the reservation, the seat number, and so forth. So every entity has attributes hiding underneath them. Okay, so in the ER model, the ER logical model, one important piece of that conceptual piece is the entity. Entities are things about which we store information. You've seen that before. Now, the other aspect of an ER logical model is the relationships, and they're represented by lines and symbols associated with lines. Okay, so for example, we see a line between passenger and loyalty account, so that's a relationship, and every relationship has a name next to it. Okay, we've had a discussion of why we need to put names of relationships. Furthermore, every relationship has cardinalities associated with it. Okay, you see these little symbols at the ends of the line. So these are cardinalities. And the cardinalities tell us what one instance of, how one instance of an entity is connected to instances of the of the other entity to which involved in the relationship. So this is a binary relationship. Remember, there was something called a degree of a relationship. There were unary relationships, binary relationships, ternary relationships, and so forth. And I also mentioned that as a practical matter, 90% of the relationships that you will encounter are binary relationships. So the cardinalities tells you how instances of one entity are connected to instances of the other entity involved in the relationship. So there were three different types of relationships that were identified: one to one, one to many, and many to many. So this particular relationship that you're seeing earns is a one to one relationship. And how do I know that? I know that from the symbols, the cardinality symbols at either end of the line. So if I had to read it in both directions, I would say one passenger earns at least 0 loyalty accounts and at most 1 loyalty account. Okay, so there could be passengers who have no loyalty accounts with the airline. Okay, now if you go to in the other direction, 1 loyalty account is earned by at least 1 passenger and at most 1 passenger. Okay, so that's what those two lines mean: the minimum cardinality and the maximum cardinality. So the maximum cardinalities determine the type of the relationship. Okay, so this is a one-to-one kind of relationship. Now let's look at a second type of relationship here between the entity flight and the entity seat. So you can see a line connecting the two. So a flight contains seats. That's the relationship. But the symbols, the cardinality symbols, are different at the two ends. So the way I would read this relationship is one flight contains at least one and at most many seats. Okay. Now if I go in the reverse direction, one seat is contained in at least one and at most one flight. So you can once again, when you talk about cardinalities, there's a minimum cardinality and a maximum cardinality. This relationship is a one to many relationship. So colloquially, informally, the way you would say it in words is one flight contains many seats, but one seat is contained in exactly one flight. So this is a one-to-many relationship, and this is actually a parent-child relationship. If you remember in our very first class, when we decomposed one list into different themes, we said that we need to put Humpty Dumpty back together again, and we did that through connected attributes that connected themes with one another, and in that context we identified parent-child relationship. So the one-to-many relationship, the one is the parent and the many is the child. So this is an example of a one-to-many relationship, a parent-child relationship. Okay. Now let's look at a third type of relationship. We have reservation, the entity reservation. So we have a reservation number and the price of the reservation and so forth. And then you have this entity flights. But this time you can see it looks a little bit different. That the line between the two entities, the relationship, is booked via, that's the name of the relationship. But you can see that the endpoints look a little bit different from the first relationship we discussed as well as the second relationship we discussed. How is this relationship different? If you look at the endpoints, here at both ends you have the crow's feet. This is an example of a many-to-many relationship. And the way I would read that relationship is one reservation is booked via 0 flights or at most many flights. Now, why at most many flights? So let's say I'm going from here to Australia. So it may not be one continuous flight. So I might go from here to Frankfurt, Frankfurt to Singapore, and then Singapore to Sydney. Okay, so there are 3 flights that the reservation consists of. So one reservation could be booked via multiple flights. And similarly, one flight, there could be many different passengers on a particular flight. So if I take one flight, is booked via at least 0 and at most many reservations. So this is an example of a many-to-many relationship. So that's the third type of relationship that you could have. Okay. Now, we will see later on how this logical structure is translated. That's the second into relations. That's the whole purpose of today's lecture and the subsequent lecture. But to wrap up this discussion of ER diagrams, let me focus on these 3 entities: person, passenger, and crew. If you take these 3 entities together, you can see that there are no crow's feet at the end of any of these lines. But a line tells you that there is a relationship among these 3 entities. This is the generalization and specialization, the supertype and subtype relationship that we had discussed in the previous lecture. So this little diagram, this little symbol over here rather, this circle with the line underneath it, is what tells me that these 3 entities constitute a supertype subtype relationship. So a person can be either a passenger or a crew member. Okay, so this entity called person has been broken down into 2 subgroups: passenger and crew. Okay, so what does the circle and the line below it, what does that represent? The circle tells me that these 2 subtypes, passenger and crew, they might overlap with one another. Why is that? But that offhand that might seem strange. How can a person be both a passenger and a crew? You could have a crew member who's not flying and they're a passenger on a flight. They're going from point A to point B, but they're not on duty at the time. So you could have a person who's a passenger, a crew, and so these 2 subtypes could overlap. Okay, that's why you don't have an X in this circle. So this is an inclusive. These 2 subtypes are inclusive. Now the single bar underneath the circle tells me that these subtypes are not complete, it's partial. That means there could be a person who's neither a passenger nor a flight crew member. Maybe it's a maintenance person, I don't know. But there's a person in the database. It's possible that there could be a person in the database who's neither a passenger nor a crew member. That's what these symbols represent. So this little discussion that we've just had using our airline reservation example, the reason I had this discussion is just to recap all the different concepts and symbols that we encountered in our discussion of the logical entity relationship diagram. With that as a foundation, we can now begin our journey of translating this diagram, this structure, into the physical model. So this is the relational schema. So we'll get this diagram into a shape that makes it more fit for implementation. That's what we're going to get into. And as I mentioned a few minutes ago, what we will focus on this lecture is nitty-gritties of how to translate the entity. Then we will get into relationships, okay, in another lecture. But an entity is a major portion, major component of an entity relationship diagram. And to implement an entity, there are all kinds of details. So if you look inside this relation, that is the manifestation, that's the implementation of this entity airplane. There are various details, and this picture doesn't contain all the details. That's what we will get into here. At the very least, you can see that the airplane, the entity called airplane, in order to implement it, I need to identify what are the different attributes. So I will have to tell the database this attribute called model number can be of a certain type. So model number, for instance, will contain letters and numbers. The capacity of the airplane will be a number. It's an okay. Similarly, for flight, this entity called flight, it has some properties. It has attributes. So one of the attributes is departure time. Another attribute is arrival time of the flight. But you can see that even though departure time is a number, arrival time is a number, capacity is a number, those numbers are not of the same type. For instance, capacity is an integer. You're not going to have an airplane with 2.5 seats, okay? Fractional. Similarly, the departure time, it has hours, minutes as two parts to it, okay? And again, it's not fractional, but there's a certain structure to time that is not present in the case of capacity. So there are all kinds of nuances about the properties of an entity that need to be dealt with. And that's the first piece of the implementation that we're going to get into in today's lecture. And then the next important piece is the R of the ER diagram. That's the relationship. That's what we will get to in a different lecture. So let's dive in and see how one goes about translating entities into the relational, into the physical model, and then we'll continue from there. So to get into the nitty-gritties of how to implement entities in the at the physical level, some of the things that we'll discuss are attribute domain, data types, null policies, primary key, and we'll do that all through examples, and we will see what all these different concepts, items mean, and why they're important as a part of coming up with a physical a relational schema from the entity relationship diagram. Okay, first things first, let's discuss what we mean by attribute domain. Attribute domain tells us what are the set of values allowed for an attribute. Okay, so for example, when go back to this entity airplane, it has the attribute capacity. The domain for capacity, the attribute capacity, so the attribute domain tells us what values are valid for this particular attribute. And that is necessary. These type of specifications are necessary so that we can maintain the integrity of the data in the database. Once we specify the attribute domain, then the database can enforce those attributes and that can enforce those constraints, properties, and maintain the quality of the database. Okay, so what are the different aspects of specifying the attribute domain? You have to specify the data type. We'll see in a minute what we mean by data type. We have to specify something called null policies, whether it's unique, and business rules. Okay, for instance, if you have an attribute called age, the business rule might say that age cannot be less than 0, and it can't be more than 200. You don't expect anyone to be more than 200 years old. So if somebody types in 2000 by mistake as a value for age, then immediately the system will flag and say, hey, you have a bad value. Look into it and maybe fix it. Okay, so these attribute domain, the different aspects of the attribute domain, these are not there. Again, I repeatedly keep saying that these are not there to make life more complicated. These are there to capture the properties of the data accurately and maintain the quality of the data in the database. So there's nothing redundant about these aspects of the attribute domain. So let's proceed further and unpack what these different aspects of the attribute domain mean. So let's look first at data types. What do we mean by data type? So here are some examples of different data types that you can have. So a data type could be numeric, string, or date time. Okay. Now, the data type tells the system, the database management system, what type of data. So, for instance, if you have an attribute called price, then you would say that it's numeric. And if you typed in some character by mistake, again, the system could flag that saying, hey, you got the wrong data type in there. So the data type tells the database management system, the software that's going to manage the database, uh, what type of data is being stored for that particular attribute. We'll see examples in a minute, but here are three examples of what a data type could be: numeric, string, and date time. Okay. Now, even within numeric, data types could be different types of numerics. So here are some examples. Yeah, these examples that we're seeing is from the SQL Server. That's the software package that we are going to use. Now, if you are using a different database management system, let's say Oracle or something else, then the data types that are supported by that particular piece of software may be somewhat different. But these are examples of what the numeric type of data could be. Okay, so among the different variants of numerics, you could have exact numerics. Okay, so tiny integer, small integer, integer, and big integer. So these are all exact numerics, different type. What is the difference? A tiny integer, its value is between 0 to 255. Okay, so what would be an example of an attribute whose data type could be tiny integer? If an attribute within an entity is age, then you don't expect anybody's age to be more than 255. So you could specify that age to be tiny integer. Why not just leave it undefined? Leave it could be any large integer as well. Well, once you specify that the age is tiny integer, then the system can allocate enough space for that and not waste space. Okay, so if age is not expected to cross 255 in value, there is no point keeping a huge amount of storage space for it. So this is a way of communicating with the database management system to tell it to manage the storage better, and also to maintain some integrity of the data. So if somebody types in a value more than 255, the system can flag it. Okay. The small integer has a different range of values. You can see how much storage each requires. Okay, in terms of value. Now, this may not seem significant. 1 byte, 2 byte. What difference does it make? But as soon as you start talking about a huge database with thousands and thousands of customers, with millions of transactions, then it all adds up. So storage may be cheap, but it's not the cost is not zero. So we do try to keep a handle on the storage required for storing the information in the database. So an example of an attribute whose data type might be specified as small integer would be flight. Okay, the distance that a flight may need to travel, an airline might need to travel on a particular flight. So two other examples of exact numerics are integer and big integer. You can see that the way they vary is the range of values that they can take. It's minus such and such, 2,147,000,000, and so forth. So the ranges are different for integer and big integer. But notice one thing common across all these exact numerics. Okay, they are integer, so that means they do not have a fractional component to them. So if you had an attribute called price, which has two decimal points, dollars and cents, it would not be proper to specify the data type of price, an attribute called price, as integer. That would be a mistake. Or if you have the weight for a particular item, then it would not be appropriate to specify its data type as integer if the weight can take on fractional values. I hope you're getting a sense of the consistency between the attribute, what values the attribute can take, and the data type that you specify for that particular attribute. Okay, so one example of the data type is numerics, and within numerics, one subtype of it is exact numerics. These are values, these are numbers which don't have fractional parts to them, and then you have these different variants of exact numerics. They take different amount of storage, and they allow you to store different ranges of values. Okay. Then there's a special type of numeric called money. So it has two places of decimal. So there's small money and money, and the difference between the two, they take different amount of storage to store. So if you specify an attribute to be small money, it will take up 4 bytes in storage. I hope you remember what this means from your MIS 301 classes. Okay, so money as a data type would take up 8 bytes, so it takes up more space, but it allows you to store a larger range of values. And notice the precision. So there are 4 places after the decimal point that it stores for both small money and for money. Okay, so it's not a huge precision. So you don't have 16 places after the decimal point, for example. But the difference between small money and money is the range of values that can be stored, and also the other difference between them is the amount of storage that it takes. And you can see examples of attributes within an entity that might be suitable for these two different types of data type. So if you have a price for a product, specifying it as small money may be appropriate because the values will fall within this range. But if you have a portfolio, a financial portfolio, you probably would need a larger range of values. And for to capture an attribute, to represent an attribute like total value of a portfolio, it might be more appropriate to specify the data type as money rather than small money. Okay. So again, then in the course of this discussion, try to get a sense of the how one goes about specifying data type. You need to know something about what values the attribute can take, and then match it, and then accordingly specify the appropriate data type when you are creating the relational schema, when you're translating from the entity relationship diagram to the relational schema. So these are the kinds of details that we will fill out. So we'll look at these different pieces, and in the end, we'll put them all back together with a whole example for a single entity, and then we'll see each of the attributes, and we will have a discussion on the data type for each of those attributes. Right now, all we're trying to do is identify the different data types that attributes can take. Okay. Another type of numeric data type is the decimal. So if you specify something, an attribute as a decimal data type, it's a numeric, it's a number, but it's stored in a slightly different format. So the way you specify a decimal is that you specify the length of how many digits will be stored, and also the precision. Okay, so the precision is the number of digits after the decimal point that will be stored, and the precision is the total number of decimal digits that will be stored both to the left and to the right. So if I have, let's say, let's pick up the pen. All right. So, we have an example on the next slide. But anyway, the precision. So if I have a decimal, so representation. So the precision is this whole, how many digits there are in total. And the scale is the number of digits after the decimal points. I think it might be easier to look at the actual example. So let's say we have an attribute, a student, an entity called student, and one of the attributes in that entity called student is the GPA. So here's the entity called student, and one of the attributes is GPA. So this is the entity called student, and one of the attributes is GPA. In order to implement this, so this is something you might see in the logical ER diagram, and if you're translating it now, you're in the process of translating it into relations for the relational schema, the physical model. So you have to specify the data type of the GPA. You have to tell the database management system this attribute called a GPA is numeric, and so on and so forth. This is the kind of data that it would have. So, if you think of a GPA, there are 3 digits to it. Okay, and we always store a GPA with 2 places after the decimal. So when I specify the data type for a GPA, I will say decimal 3,2. I hope you understand where the 3 comes from and where the 2 comes from. 3 is the total number of digits that are stored for the GPA, and 2 is the number of digits after the decimal place. All right, so that's how the data type called decimal works. If we have a data type called length, if you have an attribute called length, okay, then these are the 2 values within which the range would be stored. So if I specify the data type for length, so I have an attribute called length. So I have some entity and there's an attribute called length. And if I specify the data type as decimal 7.4, then what I'm telling the database management system is I will store this attribute as 7 digits, 1, 2, 3, 4, 5, 6, 7, and there will be 4 places after the decimal. So the decimal point will be here. I will store 4 places after the decimal, and there will be 3 places before the decimal point that will be stored. So I hope you're getting a sense of what this data type decimal 7,4 would represent. Okay. So up to now you've seen exact numerics, but there's another type of numeric called approximate numerics, and all that means is that that number can have a decimal point. Okay, it could be something like interest rate, it could be something like the length of an object, the weight of an object, and so forth. So another type of number. So it's a number, but the number can have fractional parts, fractional component to it. Okay, so these are called approximate numerics, and the 2 variants of approximate numerics could be float or real. That's the 2 data types that you could have, and they are used primarily for scientific and data engineering, but they can also show up in business applications. For instance, if you have an interest rate of 2%, so let's say you have a checking account with an interest rate of 2%, then to actually calculate the interest depending on the amount of money that's in there, if you multiply it by 2%, you will get a value that has a fractional component to it, something after the decimal point, and you may want to store that as a float or a real number. So approximate numerics are simply mean these are numbers that have fractional parts to it. Another very important data type is date and time. So when you think of business applications and you're creating a database to store, to support the business application, you could have different entities, and within those entities, very likely that date and time will show up as an attribute. For instance, if you make a reservation, continuing with the example that we're using, if you make a reservation, clearly that there will be a date and time associated with the reservation. If you think of a flight, its departure time, there would be a date and time associated with departure time. So if you think of the attribute called departure time, its data type will be date and time. Okay. Similarly, for arrival, there'll be a date and time associated with it. If you make a purchase, the transaction would have a date and time associated with it. So a very common data type is date and time. They could be separate, they could be together, but date and time are 2 important types of data that are stored in a database, particularly in a business application. And there are certain variants of this attribute. So let me pick up the laser pointer again so as not to clutter up the chart. So one of the data types is date, that corresponds to one of the data types that falls in this category of data type. There's a data type called date. There's a data type called date time. There's a data type called small date time. There's a data type called time of day, and date time with an offset. So little variants, and as I mentioned, what variations of date as a data type are available to you varies from system to system. So this is with SQL Server. If you are using Oracle or some other database management system, the types that are available to you that fall in the category of date and time might be somewhat different. Okay, so I will not go through all these details and let's repeat them what you're seeing in the slide. Maybe you can pause the presentation at this point and go through the variants of date and time. The way they vary is the range of values that they admit. For instance, the date itself, the range of values that it can handle is January 1st, 0001 to December 31st, 9999. If you look at date and time, then the range of values again a little bit different. Small date and time. So if you compare these different variants of date and time, if you look over here, you can compare them by the range of values that are valid for that particular data type. That's how they vary. Okay, so I will not belabor you by repeating what all these different values are. You can pause the presentation and take more time looking at the different values that are covered by the different data type variants of the date and time. The next important variant, or rather, the next important data type. So you've seen numeric data types, and then there are exact numerics, approximate numerics, and so forth, and date and time. So all the discussion of the different data types that we have discussed so far fall in the numbers category. So they're all numbers of different forms. Okay. The next broad type of data that you can have in the database is character strings. Okay, and again here, just like you had variations of numbers, you have variations of character strings, and we'll see what some of those variations are, and I think you will get a sense of why are these different variations. Why do we have to look at these different variations? What's the benefit of having these different nuances of character strings? Okay, so first is you have a data type called chars, character, right? And here what char means is it's a fixed length of characters. Okay, n defines the length of the string and it must have a value between 1 through 8,000. So if you specify an attribute as having the data type char, okay, and then with a certain number of digits, then you're saying that this attribute will be so many characters long. Okay, for example, zip code could be specified as character 5, so it's five digits long. Credit card numbers are always 16 digits long, so we say 16 digits. The important thing is these are characters. That means they could be numbers or letters. Okay, and they are of a fixed length. So if you specify an attribute as char, it's of a fixed length of characters. So what happens when data entered is less than n? So if I specify an attribute as character 10 and the input that I give is less than 10 characters long, then data is stored you pad up with spaces at the end. Okay, so I input 7 characters, but I have specified the data type as character 10. Then those remaining 3 spaces, the remaining 3 characters will be padded up with blanks. Okay. If I enter more than n, so if I specify an attribute as character 5, and then I type in 7 characters, the last 2 characters get chopped off. So data gets truncated if I enter a string that's too long, longer than what is specified in the data type. Okay. Now, instead of specifying an attribute as being of type char, I can specify it as being of type var, variable character, and then I give n. Okay. I think you can guess what the difference is between char and var. If I specify an attribute and I tell the database management system, hey, this particular attribute is var char 10, variable character 10. That means I'm telling the system this attribute could consist of anything from 1 character to 10 characters. Okay, so if I say var char 10, then I'm telling the system that this attribute could consist of anything from 1 character to 10 characters. Okay, so as some examples, you have all cities don't have the same name. Okay, so if I specify this attribute called city name, so I have let's say an entity called city, and one of the attributes of city is the name of the city, and when I'm translating from the logical entity relationship diagram to the physical model, I tell the system, hey, this attribute called city name is var char 85, or var character 85. That means the longest city name that the system will accommodate is 85 characters long. So if I enter a city name that is less than 85 characters long, then less space will be used. So there's no padding up at the end with extra characters. So this basically, you can get, what this does is it saves space. All right. So, however, if I enter a value that is more than n. So if I enter a city name that's more than 85 characters long, highly unlikely, but suppose there is such a city that is more than 85 characters long, and I try to enter that, then anything after 85 characters will get chopped off, will get truncated. So that's how the system will handle extra long inputs that I try to give. Okay. Now another variation of character of text is is this data type called text. So the difference between char, var char, so you have a data type called char, you have a data type called var char, and now you have a data type called text. So these are all variations of strings. What's the difference? The text can be hugely long. So you can see that if I specify a particular attribute as text, then I can put characters and numbers, numerics in that string, but that string can be really very, very long. You can see this number over here. It's just really limited to the amount of storage that you have. And the examples of attributes for which you might specify a data type of text is product details. So you have an entity called product. So let's say you have a box that that represents a product, and one of the attributes of the product, you could have product price, product name. One of the attributes could be product details. So that consists of a bunch of text. So you can go to any website for Home Depot, let's say, and you're looking at a product. You will have a short description of the product, but then you can have a long details about the product. So that takes a lot of text. Okay, so once you specify that a particular attribute is of data type text, the system allows you to put in a long string. That's basically what it allows you to do. Another example of an attribute whose data type might be text is an email message. So the message itself can be stored in the database. Okay. All right. So thus far, the discussion that we've had is about data type. So let's get back to where this discussion started. Okay, so the whole discussion that we are having is about attribute domain. So entities have attributes, they have consist of attributes. So when I'm trying to specify an attribute, when I'm trying to implement an attribute, there are a whole lot of things about the attribute that I need to specify. One of the things that I need to specify is, the things that I need to specify about the attribute is the domain of the attribute. What kind of values can it take? One aspect of the value that an attribute can take is the data type, and that's the discussion that we've been having so far. So we could tell the system that the attribute is of type numeric, and within numeric I could say that it's integer, float, and so forth, or character or date time. Okay, so that one of the aspects of the attribute is the data type. What kind of data will be stored in the attribute itself? So next, in terms of the attribute, remember we are talking about one single attribute within an entity. These are all the things about the attribute that we need to specify, or we might want to specify in order to get to the actual implementation. So first is the data type. Will the attribute consist of numbers? If so, what type of number? Will it contain a character? Will it contain characters? If so, what type of character string? Is it long, short, things like that? Character, variable, character. That's the discussion that we've had so far about the data type. The next aspect of attribute domain, what is it about the attribute value that I need to specify, is what is called null policies. So let's see what we mean by that. So I think you can guess again what null policies might mean. I have to tell the database, I have this attribute. When I look inside the database, it may or may not have a value. I may not always know a particular value. Okay, so let's see what we mean by null policies. Let me get back to the slide where it was. So here's null policy. So a null policy defines whether data must always be present for all instances. Okay. For example, For all students, the first and last name. So let's say you have an entity called student. Okay, when you're entering a student, there are two attributes of a student: is student first name and last name. Those are two properties of the entity called student. Now, if we say that first name and last name null is not allowed, then we are saying that when I enter a new student, I must know the first name and last name. I cannot enter a student without knowing the first name and last name. And that makes sense. I can't imagine a situation where you're entering a student into the database and you don't know the first name and last name. Okay. Now, by contrast, notice that if you have an attribute called middle name, first name, middle name, last name, okay, not all students have a middle name. So as far as middle name is concerned, null is allowed. That value can be null. But the first name and last name cannot be null. The first name and last name cannot be null. Okay. Now here are some important things to know about the null, the term null. Very often students mistake null as zero. So if the policy says that a particular attribute can be null, okay, it doesn't mean that the value is zero. Okay, null is not the same as zero. Null means the data is unknown or not present. It's not present. Okay. For instance, if you have a student and the social security number is not required, so there are privacy requirements, social security number. So you have an entity called student, okay, and you have an attribute called social security number. Then we could say that null is allowed, that value is known, but we not put it in the database. All right, for a particular student, let's say a student who objects to having the social security number. For instance, when I go to the doctor's office, it's very common for the doctor's office to say, please put in your social security number in this form, and I tell them the government policy does not, it permits me not to give my social security number. So whatever database they have, that value would be null for me. They can't put a zero for my social security number. That's not a right thing to do. So null is not the same as zero. Okay, it simply means that the data is not known. So similarly, null doesn't mean space. Okay, so it doesn't mean that you fill it in with blank spaces. A blank is a valid value. So null means the value is not known, it's not present. Okay, so just remember this, because when it comes later on, when in the subsequent classes, when we get to implementation and actually doing manipulation, retrievals from the database, this will make a difference. A null is not the same as zero. Null is not the same as blank. Okay. Here is another aspect of the attribute domain. So let's again just quick back to where we started our discussion. So we are still looking at different aspects of attribute domain. What kind of values can an attribute take? So the discussion we've had so far is data type is an aspect of the attribute domain. We are telling the system, the database management system, that this particular attribute can take certain types of values. The next thing we discuss is we tell the system, hey, the value that the attribute takes could be null or may not be null. Okay, so null policy. What's the policy regarding nulls? The next aspect attribute, the attribute the values that the attributes can take is uniqueness, meaning does the value need to be unique? So you have a particular attribute, it takes certain value. Does the value have to be unique? Uniqueness policy. Let's see what we mean by that. So this is the primary key, or the uniqueness policy. So every instance must have an identifier. So let's I think you can again, let's see. Let me pick up the pen here. Yeah. Okay. So I have an entity called student, and it has certain attributes. All right. So I will just list those. Signify those with these rows over here. So you have the student first name, last name, okay, maybe date of birth, address, and so forth. Okay, so you can think of a table of students, and they have these attributes. These are the properties of the student. Now, within this entity, how am I going to pinpoint a particular student? I must be able to pinpoint a particular student when I try to retrieve information. Okay, similarly to if you think about the airline reservation example that we've been using, I need to be able to retrieve a reservation. So just think about how if you go to any airline reservation system, let's say United Airlines or American Airlines, you have made a reservation and you want to retrieve it to change it or cancel it or what have you. What does the system want to know? It wants to know the reservation number, that 6-digit number or that 7-digit number that your airline has given has used for the reservation. So it typically asks you for that reservation number. That's what it uses to identify that your specific reservation. So I need some way to be able to identify, in this case, a particular student. So let's say I put in my G number. As a George Mason student, we know that every student has a unique G number. No two students will have the same G number. So if I know the G number of a student, I can uniquely identify that particular student in my entity set. Okay. So here is an attribute called G number. However, one restriction or one property of that attribute in terms of the values that it can take is that it must be unique. Okay, so you can't have two students with the same G number. So here is a situation where when I tell the database management system I have this entity called student, and within it here is this attribute called gnum, I will tell the system that the gnum is unique. And then once I tell the system that, the system will ensure that if I ever try to put in a student with a duplicate G number, it'll flag it. It'll say, sorry, you're conflicting with the student who already exists in the database. Okay, so here are some examples of attributes in a business database uh, uh, which might be unique. Okay, so these attributes are called identifiers of primary keys. So, for example, the social security number, student ID number, account number. So, if I access my electric utility company and I have questions about a particular bill, typically the first thing the system comes back and says is, give me your electricity account number. Okay, and then if I don't know it, which I usually don't remember, then it'll ask for other things like give me your phone number, maybe to try to find me through my phone number. But I hope you're seeing the importance of attributes that are unique. Every entity must have a primary key or an identifier, otherwise I can't find out any particular specific instance of that entity. Okay, and those attributes which help us do that, these are specified to the system as being identified as a primary key, and the way we do that is by saying that they are unique, either by saying that hey, they are primary keys, or the value it's unique. So the uniqueness of the value, uh, if the value needs to be unique, I need to tell the system that in terms of the attribute domain. Okay, clearly first name and last name will not be unique. You could have multiple students with the same first name, multiple students with the same last name. They could have multiple students could have the same date of birth. So none of these other attributes would be specified as unique, whereas G number would be specified as unique as the data type for that attribute, a G number. Okay. Now, within this concept of a primary key or this unique identifier, there's this related concept called candidate keys. So candidate keys are simply attributes that could possibly be unique, that could possibly serve as a primary key. Okay, so for instance, for a student, okay, if you have an entity called student, and there are various attributes for this entity called student. All these rows represent attributes, all these different things in the box. So let's say you have the following attributes all as part of this entity called student. You have the student's social security number, so you have SSN as one attribute. You have the ID number of the student, that's something like the G number. You have the telephone number, and you have the email address. So from what we know about student information, I think it's reasonable to say that social security number is unique. No two students will have the same social security number that we know. Okay, and then the student ID number, the G number, we also know would be unique. Telephone number, that I don't know for sure, but very likely it's unique. It's unlikely that two students would have the same telephone number, particularly if it's a cell phone number. And of course, two students would not have the same email address. So all these attributes, okay, there could be others like first name, last name, date of birth, and so forth. But these four attributes, if they are part of the entity student, these are all what are called candidate keys, meaning that each of these are unique and they could possibly serve as a primary key. Candidate keys are simply attributes or combinations of attributes that could possibly serve as a primary key as for the entity. Okay. So now that we know what a candidate key is, the primary key would be selected from among the candidate keys. So if I know these are the possible attributes that could be a primary key, how do I select one of them as being to be the primary key for the entity? After all, we said that every entity must have a primary key. Otherwise, I cannot identify a specific instance of that entity. Okay. So what are the criteria that you need for selecting a primary key? What are the factor that you should consider? Okay. So here are the different factors. One is whether or not a null is allowed, whether there are security concerns, whether these values can change frequently, whether they are verifiable, and whether they are fixed with or not. Okay. So all these aspects or properties of the candidate key, they're not equally important. So let's look at each one in turn. So we had said social security number, ID number, telephone number, and email. These are all attributes of the entity student, let's say, and they could possibly serve, because they are unique, they could possibly serve as a candidate, as a primary key. Okay, so which one of these four would be the better one to pick as a primary key? So let's look at a social security number. I know that null is not allowed. You can't have a student without a social security number. Okay. Is there a security or a privacy concern? Yes, we know that from regulations that it's maybe not desirable in certain circumstances, or the student may not want the social security number divulged because of identity theft situation. 20 years back that was not a major concern, but now it is. Okay, so yes, the social security number is unique, but for security reasons, privacy reasons, it may not be a good choice as a primary key. Change is where obviously if the primary key can change, that causes problems, because there might be confusion in terms of uniquely identifying a particular student in the database. So we want the change to be very rare, if at all. Okay. So yes, the social security number does not change, and it remains the same for life. So that's good. That's a good property of a candidate key to make it a suitable primary key, suitable for a primary key. Yes, I can easily verify a social security number, and it's a fixed width. I want fixed width because in terms of managing storage, in terms of implementation, I always prefer the fixed width. Okay, the social security number has a fixed width. Now, if I go to an ID number like your G number, null is not allowed. That's good. Is there a security or privacy concern? No, G numbers are easily shared. The government really doesn't care. G number is only relevant within the university, so the need to protect it in terms of privacy and so forth is less extreme. Change, it doesn't change. Okay, it's easily verifiable, yes, and it's a fixed width, yeah. So if I compare social security number and the G number, I hope you'll agree that the G number in the context of George Mason is a better choice as a primary key rather than the social security number. Okay. Now, if I think about the telephone number of the student, null is allowed. Yes, there could be a student who doesn't have a cell phone. Okay, so if the null is allowed, then notice that telephone number is completely unsuitable as a primary key, because if I'm using the telephone number to identify a student, and the telephone number can be null, then I can't identify the particular student. So that telephone number is not a good choice as a primary key. Okay. In terms of privacy concerns, maybe they are, maybe they aren't. That depends on government regulations. Change is rare. No, it's not. Mobile numbers change all the time. So trying to identify the same student if their telephone number keeps changing can be problematic. Okay, so I hope you're seeing that some of these characteristics of the candidate key are what can be used to determine if I have multiple candidate keys. Sometimes you have a situation where a particular entity has only one candidate key, and then that's going to end up being the primary key. But if there are multiple candidate keys, go through some reasoning, the kinds of reasoning that you see over here to determine which one of the candidate keys. So if I look at all the options, all these values over here in the table, then among the four different possible candidate keys, it seems like the G number, the ID number of the student, is the best choice for the primary key. So from among the four different candidate keys. So I hope you got the sense of what is a candidate key and how to pick one of the candidate keys. If there are multiple candidate keys, how would one pick one of them to be the primary key? Okay. Okay, so now in this context, we've already identified what a primary key is, what a candidate key is. There's another variant of this primary key. It's called a composite key. In the examples that we have seen so far, in this case, the social security number, ID number, and so forth, okay, the example that we have discussed so far, the candidate key consisted of one column, one attribute. Okay, so it consisted of one attribute: social security number, ID number, telephone number, or email. So it's one attribute. Okay. Now, here you have a situation where you have an entity. The entity is a course in this case, and the course has different attributes. In this case, there are four attributes: the subject code, the course number, the name of the course, and the credit hours. Okay. So here you have an entity called course with four attributes. What would be the primary key for this particular? Every entity must have a primary key because that's the attribute I would use to uniquely identify an instance of that entity. In this case, the entity set is course. So if I am to identify a particular course, an instance of that entity, I need a primary key. Okay. Now, if I use only the subject code, that's going to be a problem, because if I simply say MIS, that could identify multiple courses. Similarly, if I use just the course number, let's say 310, that's also a problem because it could cut across subjects. So here you have 310 in MIS, you have 310 in finance. If I just say 310, I'm not able to uniquely identify an instance of a course. So what do I need? I need the subject code as well as the course number together. So if I say MIS 310, that uniquely identifies an instance of a course. If I say finance 310, that uniquely identifies another instance of the entity course. Okay, but notice that I now have to specify two attributes together. Okay, so this is an example of what is called a composite key. So that's a variation of key. A lot of the time, the key will consist of one attribute, but you will soon see that there will be instances that arise not infrequently where the primary key consists of multiple attributes. Okay, so we've looked at different pieces of something called the attribute domain. So just to remind you of where all this discussion started, the origin of all this discussion. So we were looking at attribute domain. So an entity consists of attributes. That's the very lowest level of detail that you have to specify as you're building up the physical model. Entities consist of attributes. So what is it about attributes that I need to specify? This thing called the attribute domain. What values can the attribute take? And just saying what values it can take, there are different dimensions to the word value. So we have data type, a value as a data type. There are null policies associated with it. There is the uniqueness aspect of values, and then there are business rules. We haven't yet discussed business rules. We have discussed these three so far. So let's in pieces, one by one. So let's put all these our discussion of these three aspects of the attribute domain. Let's put that together through some examples. Okay, so here's the first example. So in the ER diagram at the logical level, so at the first level, so from the narrative to the logical ER diagram, let's say we have an entity called student. So here you see the name of the entity and the various attributes of the student that are stored in the database. You have the name of the student, address, date of birth, SSN, ID number, telephone, and email. These are all the attributes of the student. Now, in order to get from this logical structure to the physical structure of the database, so notice in going from here to here, this is one step that I need to do in order to get from the logical ER model to the physical ER model. So let me just go back again to the very beginning. So I think it's important to get a sense of where we are in this modeling journey. So coming back to the start, so here we are. We have the entity relationship diagram, the logical model. We are now in the process of translating that to the physical model, going from here to here. So we are continuing our journey of data modeling process. So we are going from here to here, and we are filling in the details of this entity. In order to implement the entity airplane, I have to specify things about its attributes, and that's the discussion that we are having. What do I need to do in order to specify the physical details of this entity? Okay, so let's get back to the example that we are using. Okay, so we have this entity called student. This is what we would see in the logical model. Here's the translation to the physical model, the relational schema. So again, you have a box that represents the entity. Every entity must have a name. So here we have the name of the entity student. And we have the attributes. So do you see this name, address, date of birth, all of those things appear again over here. This is the list of attributes that correspond to the attributes of the student. But now we are providing additional details. So this is the attribute domain for each of the attributes. So let's first take name. We are telling the system that this attribute called name, its data type is var char 50. So it can be at most 50 characters long, but the length will vary. So some names will be shorter than other names. This database will not handle any names that are longer than 50 characters. By not handle, I mean if you type in a name that's longer than 50 characters, it will just chop it off. Okay. Similarly, the address is variable character, 250 characters long, and that makes sense. Addresses are longer, but addresses also vary. Some are short addresses, some are long addresses. So specifying the data type as variable character makes sense. Okay. Now notice that some attributes are in bold, some attributes are not in bold. Okay. The attributes that are in bold, null is not allowed. That's another aspect of the data type that's another aspect of the attribute domain that we are specifying. Okay, so when we say name is variable character 50 and it's written in bold, what we're saying is the name can be up to 50 characters long and you must provide a value for it. It cannot be null. By the same token, you see telephone number over here. It's character 10. Character 10 means it's a fixed length 10 character, but it's not in null. Meaning null, it's not in bold rather. So that means null value is allowed. You could have a student with no telephone number. All right. So this is what the attribute domain. These specifications that you're seeing over here are the attribute domains for each of these different attributes. And now let's come to this special attribute. We went through a discussion to conclude why is, even though social security number is unique, email is unique, telephone number is unique, ID number is unique, why did we pick ID number as the primary key? Or the identifier. And I won't repeat the discussion over here, but you can see in this picture, you have this one attribute called ID number. Its data type is character 8. It's in bold. That means null values are not allowed. And it's specified as the primary key, PK, the letters PK. Now, where do all these symbols, this boldface, underlining, and all that? There's just the software that we have for this course is Physio, and if you draw the relational schema using Visio, once you specify to the software that such and such attribute, in this case ID number is a primary key, it will make it boldface and so forth. So this is not something that you have to do manually. Typically there are software packages that automatically do these things for you. Once you specify the data types and the uniqueness policies and so forth. Okay, so I hope you're seeing what level of detail has to be specified to get from the logical model to the physical relational schema. And we haven't even gotten to relationships yet. We're just still on entities. So a lot of detail has to be specified in order to implement a database, and we are in the process of identifying those details. Okay. So here is another entity, course. So this picture on the left is what you would see in the logical model of the entity relationship diagram. So you have the name of the entity called course, and you have all these attributes, subject, code, course, and so forth. Notice that there is no concept of a primary key. We haven't yet really identified anything, those kinds of details over here. So there are all these attributes. Now to translate that to the physical relational schema, notice that again, the entity is represented by a box. Every entity must have a name. So here's my name for the course. And the attributes that you had for the course are repeated again in this box. Obviously, there would be those are properties of the entity. But now we have specified the domain, the attribute domains for each of these attributes. What's the domain for each of these attributes? So course name is variable character, it's up to 40 characters long, and because it's in boldface, I know that a null value is not allowed. So you can't have a course without a course name. That's what we're saying. Okay. In terms of credits, what we're saying is the credit hours is decimal 2.1. Again, it's in bold, means null values are not allowed. We don't allow a course to appear in the database without its credits being either a 3 credit, 4 credit, so forth. Now, the fact that you see a decimal over here, 2.1, what this is telling me is there could be courses that have fractional credits. For instance, you could have a course that is 1.5 credits. Typically, we have 2 credit courses, 3 credit courses, and so forth. But I know of situations, examples where universities or colleges have half a course, so 1.5 credit, 1.5 credit course. If that is allowed, if a university does not allow fractional credits, then of course we could say it's decimal 2.0. Okay, but here when you say 2.1, that means fractional values are allowed. You could have, for instance, a 1.5 credit course. Course description, again, it's long. It could be so we're saying it could be up to 500 characters long. Again, the boldface tells me that I cannot have a course in the database which does not have a description. Okay, so here are all the other attributes. Let's take. So here's another attribute called additional fees. For instance, there are certain lab courses for which some extra money has to be paid, and the data type is small monies. If you go back to a few slides previously, you can look at those 2 different data types for money. One is called small money, and the other is called money. The difference between the 2 is the range of values that they can take. Okay, so this is what the data type is. Now coming now to these remaining 2 attributes, subject code, course number, both are character 3 each. The boldface tells me that they cannot be null. You can't have a primary key that's null. If a primary key is null, then I'm not able to identify a specific course. Okay, so here we have subject code and course number, but there are 2 attributes you see over here, and both have the letter PK next to them. This tells me that my primary key for the entity is a composite primary key. It consists of these 2 attributes together. That's the composite primary key. And where's the example? This is the example that we had discussed a couple of minutes back about a composite primary key. And later on, as the course progresses, you will see lots of other examples where you have a composite primary key. It's not that uncommon. Okay. All right, so with that, we'll finish our discussion of this particular class, and we'll continue the next time.